Have you ever just looked up at the sky and wondered what actually separates our thriving green planet from a dead, frozen rock drifting through space? It's super easy to think of the sky above us as just empty space. But, it is far from empty. In this explainer, we're going to explore Earth's atmosphere, not as some big void, but as a highly active, multi-billion-year-old life support system. It's literally a dynamic physical structure that simultaneously acts as a thermal blanket, a radiation shield, and a chemical factory all rolled into one.
Okay, let's dive into this. Here's our flight plan for the explainer today. First, our invisible life support. Second, journey through the layers. Third, the ultimate planetary shield. And finally, human impacts and the future.
All right, starting right off with Section 1, our invisible life support. Just think about this staggering number for a second. 5.15 quintillion kilograms. That is the actual physical weight of Earth's atmosphere. But here is the really mind-bending part we're discovering together. Despite reaching tens of thousands of kilometers into space, 99% of this immense mass is crushed down by gravity into a razor-thin shell just 30 kilometers above our heads. To put that into perspective, relative to the Earth's size, that's thinner than the skin on an apple. Crazy, right? And the air inside that tiny, thin shell, it isn't just some random mix of gases. It's actually a highly specific, biologically maintained cocktail. We're talking about roughly 78% nitrogen and almost 21% oxygen. If life were to suddenly vanish from Earth tomorrow, this delicate balance would completely collapse, and our atmosphere would slowly revert to a toxic, carbon dioxide-dominated state, basically turning into the absolute worst neighborhood in the solar system. Now, it took billions of years of biological and geological heavy lifting to build this atmosphere. Earth's early air was totally toxic, but right around 2.4 billion years ago, these little photosynthetic cyanobacteria sparked what we call the Great Oxidation Event, slowly pumping oxygen into the sky. And so the absolutely crucial takeaway here is that this rising oxygen eventually created the stratospheric ozone layer. Once that UV shield got thick enough, roughly 450 million years ago, life could finally leave the oceans and actually walk on land.
Moving right along to Section 2, journey through the layers.
So Earth's atmosphere is structured into 5 main layers, and they're separated by these transition zones called pauses. The temperature trend across these layers actually zigzags. It drops, then rises, then drops, then rises again. And this isn't just random. The temperature reverses direction at each boundary based entirely on exactly where solar energy is being absorbed by different gases.
We all live in the lowest layer, right? The troposphere. Down here, the sun heats the ground, and the ground heats the air. And as you go up, it gets colder. This warm to cold temperature gradient causes air to rise and fall, literally driving every single weather event on Earth. But right around 12 kilometers up, we hit the tropopause. Think of this as a giant, physical lid. It stops rising air dead in its tracks, totally preventing our storms and our precious water vapor from just evaporating out into the vacuum of space.
Right above that lid is the stratosphere. And here, the logic completely flips. The ozone layer lives up here, and because it's actively absorbing intense UV radiation from the sun, the air actually gets warmer the higher you go. This creates a temperature inversion. So warm air sitting super comfortably on top of cold air. That stops vertical mixing. It creates perfectly smooth, stable skies, which, is exactly why commercial jets cruise up here to avoid all that turbulence. Pushing even higher, we enter the mesosphere. Now, without the ozone to absorb heat, temperatures just plunge to a bone-chilling minus 100 degrees Celsius at the top. It is literally the coldest place in the entire atmosphere. Yet, and here's the cool part, this freezing layer is where the friction of the air is just dense enough to vaporize 40,000 tons of space rocks every single year. It's what creates those fiery shooting stars we see from the ground. It's also home to these super rare electric blue noctilucent clouds, which are the absolute highest clouds on Earth. Then we run into the wild paradox of the thermosphere. Up here, solar X-rays just blast the sparse gas molecules, jacking their kinetic energy up so high that temperatures technically soar over 1,000 degrees Celsius. But because the molecules are so incredibly far apart, there's virtually no thermal transfer. So the International Space Station is orbiting right in the middle of this 1,000-degree heat, but it doesn't actually feel hot at all. Pretty wild, right? Which brings us to Section 3, the ultimate planetary shield. This whole system is a massive, multi-layered defense grid. We know it blocks lethal UV radiation and vaporizes meteors. It also buffers us against the wild 280-degree day-to-night temperature swings they experience over on the moon. But critically, the sheer physical weight of all this air maintains our surface pressure. I mean, without it, water on the summit of Mount Everest would boil at just 70 degrees Celsius. And without the atmosphere entirely, our oceans would quite literally just boil away into space. And extending even further out is Earth's magnetic field, the magnetosphere. This thing deflects solar winds that are traveling at a blistering 800 kilometers per second, keeping them from stripping our atmosphere away completely. Closer in, solar radiation creates a plasma-filled region called the ionosphere. This is actually the layer that bounces high-frequency radio waves back to Earth, which, by the way, is exactly why your AM radio works so much better at night. And when intense solar storms hit this layer, like those historic super geomagnetic storms we all saw in May of 2024, it literally paints our skies with the auroras. All right, on to our final section, Section 4, Human Impacts and the Future.
We really have to ask this question directly. Is the ozone hole actually healing? You know, humanity's relationship with the sky has been this intense dynamic of incredible technological threat, but at the same time, unprecedented global triumph.
And the data here is just phenomenal. In late 2025, the World Meteorological Organization confirmed that the Antarctic ozone hole was the 5th smallest it's been since 1992. Like Palalej points out, the ozone layer is well on track to recovery. By coming together back in 1987 to sign the Montreal Protocol and ban ozone-depleting chemicals, humanity literally saved its own planetary shield. Honestly, it is perhaps our greatest environmental success story. However, the newest science shows we really can't look away just yet. An April 2026 MIT study revealed that hidden chemical leaks from industrial feedstocks, these are chemicals still permitted for use in making plastics, well, they're leaking at much higher rates than anyone expected. Combine that with aluminum particles and black carbon being deposited by our rapidly booming commercial space industry, and scientists estimate we could actually delay that hard-won ozone recovery by up to 7 years, so a real step backward there. This also reveals the incredibly counterintuitive vertical fingerprint of climate change. As we pump more greenhouse gases into the air, the troposphere down near the surface traps that heat and warms up. But because all that heat is getting trapped below, way less infrared radiation reaches the layers above. This means the stratosphere is actually cooling down. And even higher up, the thermosphere is literally shrinking. Its density has dropped by 10% since the 1970s. This reduces the atmospheric drag on our satellites, which totally changes how long they stay in orbit. The entire vertical structure of our sky is literally shifting. To truly understand the stakes here, we really only have to look at our cosmic neighbors to see exactly what happens when a planetary shield fails. Look at Mars. It lost its internal magnetic field billions of years ago. The solar wind just completely stripped its atmosphere away, leaving this freezing, radiation-blasted vacuum. Venus, on the other hand, suffered a runaway greenhouse effect, resulting in crushing atmospheric pressure and a 465-degree surface that can quite literally melt lead. No thanks. Earth's atmosphere is an absolute masterwork of natural engineering. It is just perfectly tuned. But we are the very first species in Earth's 4.5 billion year history with the technological power to both break our planetary shield and, as we saw with the Montreal Protocol, the power to heal it. So, the ultimate question we are left with is this: will we protect the invisible force field that makes literally everything we know possible? Thank you so much for exploring this with me today, and I'll catch you on the next explainer.